Now we can extend this concept of electron domain geometry and molecular shape and molecular geometry to molecules that are larger than ones that simply have a single central atom. The way that we do this is by breaking the molecule into sections and evaluating the central atom of each section. So let's go through a quick example of this. If we look at this molecule here, this is acetic acid. It's a very common molecule. It's the main component of vinegar. If we take a look at this, we wouldn't initially say that there was one central atom with just a single set of atoms bonded to it, but we can break it into sections that have a clear central atom. And if we look at this, we can evaluate it first on electron domain geometry. The carbon on the left has 4 electron domains in the form of 4 bonds. The center one has 3, one of them being a multiple bond. And the oxygen has 4 electron domains, but 2 of them are lone pairs. Now, the predicted bond angles that I would get from just the electron domain geometry hold, and that would help me to arrange, if I was building a model, to arrange the atoms in space appropriately. However, now I can look individually at the central atoms of these sections and evaluate the molecular geometry of those. So if I look here at this carbon on the left, the electron domain geometry is tetrahedral. There's no lone pairs, so the molecular geometry is also tetrahedral. The central atom, the electron domain geometry is trigonal planar, and there's again no lone pairs, so the molecular geometry is trigonal planar. Finally, however, the oxygen, its electron domain geometry is tetrahedral, but there are 2 lone pairs, so I would refer to this geometry as being bent. So that's how we would extend this concept to larger molecules. There are also a couple other factors we need to keep in mind when we are extending this model to try to draw molecules more in accurate 3-dimensional space. The first of those is to look at the effect of lone pairs on bond angles. So it turns out that when we look at electron domains, lone pairs as an electron domain are a larger electron domain and exert a greater influence than single bonds. So if we look here, if we have a nucleus and we drew the space occupied by a non-bonding pair or a lone pair compared to the space occupied by a bonding electron pair, which is shared between 2 nuclei, we can see that the lone pair occupies a larger region of space. And as a result, it exerts a larger influence on its surrounding electron domains. The net result of this is the compression of adjacent bond angles that are adjacent to lone pairs. So not the bond angle between the lone pair and another bond, but between 2 other bonds when they are near a lone pair. So in this case, if we compare the bond angle in methane, CH4, that's 109.5. That's the normal bond angle predicted by the electron domain geometry. However, in ammonia, where one of those electron domains is a lone pair, we see compression of the bond angles between the other NH bonds because the lone pair takes up a larger amount of space and pushes those other bonds closer to each other. In a case where I have 2 lone pairs, that effect is even more magnified in water, where now the HOH bond angle is only 104.5 degrees. So the overall point here is that bond angles are compressed by the presence of a lone pair. And again, these aren't the bond angles between the lone pair and another bond. It's between other bonds that are adjacent to the lone pair. Turns out that multiple bonds have a similar effect on bond angles. Because a multiple bond contains more than just one shared pair, it's 2 shared pairs, if it's a double bond, or 3 shared pairs if it's a triple bond. And as a result, multiple bonds also occupy a larger region of space and thus exert a greater influence than single bonds. This is illustrated here. So if we look at the carbon-oxygen double bond here, that occupies a larger region of space, and so it compresses not the bond angle between the carbon-oxygen double bond and another bond, but the angle between the adjacent bonds. So the CCl and CCl bond, that angle is compressed from being 120, which would be the normal trigonal planar bond angle, to being only 111.4. And that's simply an effect from the larger region of space that's occupied by that double bond pushing back on the other two bond angles. So it increases the bond angle between the double bond and the other bonds, but it compresses the other bonds' bond angles. And so that's the net effect here as well. So lone pairs and multiple bonds both act to compress bond angles between adjacent bonds.